Okay. Previously we discussed different methods of analyzing some relations between different variables. And today we will discuss a new method that is quite different from those that we discussed previously from regressions, but that solves more or less the same problem, but with a bit different approach. So today we will discuss decision trees and related algorithms. Let me recall that previously we discussed regressions. And in regressions, we said that we have some data with several variables. For example, we have variable x1, x2, and so on, I don't know, xd. And we have some variable y, and we have some data. Here can be some numbers for simplicity. And we have some value here. And we discussed regression models when we assume that there is a linear relationship between variable y and all these variables that we use to predict this y. So we used some linear model, something like this. So to simplify, I omit any categorical variables. I just use numeric variables, but this is just to simplify the notation. So we can think about this model as a model that solves a kind of prediction problem. So if you know all values of these variables, x1, x2, and so on, xd, and if you fitted your model to some data, so you know these values, these betas, then you can use this relation to predict the value of y. So for example, if I have some new object, for example, new participant of some research, or some other new object or new sentence in a text, for which I know only the values of these variables that are denoted by x1 and so on xd. Then I can use this formula to predict this value, even if it is unknown. Actually, we can think about these models in different ways. We can think about them as something that is really models the reality. So we can believe that in reality, we indeed have something that is close to this linear relationship. And we try to find the actual form of this relationship, the actual coefficients from the data. So there is some true law that, and according to this law, the value of y is defined by the values of these variables in this way for some true but unknown values of these coefficients. And we want to find these coefficients. And this is an approach that is used in statistics and in some applied versions of statistics like econometrics. In econometrics, they are really they really bother with correct estimating of these values. But we also can consider this kind of problem as a purely prediction problem. So we want we are not assume that we are not interested in the true law, the true law that allows us to find y using these values x, but we are interested in a good prediction algorithm that allows one to predict the value of this y for some new object for which we know the value of this x's. And we are not interested in how it works. We are happy if it is just a black box, but if the predictions are good, then we are happy. In this case, we are more into the domain of machine learning rather than purely statistical domain, because in statistics, we usually say that we are interested in these coefficients, in how our model actually works. In machine learning, we just are interested in the quality of predictions. So we can think about it as in machine learning, it is called supervised learning problem, when we have to find some ways to predict y based on these values of x. And sometimes this approach allows us to use a wider range of models and do not stick with this linear model, because it is good, but it is too restrictive sometimes, because not all relations between variables can be described as linear relations. Not every relation is linear relation. It is possible, for example, that we have something different, that we have, for example, something like this. This is x1 and this is y. This is not a linear relationship, but this is a relationship. So if we just use a linear model, then we do not see any relationship between y and x here. Sometimes we can augment our linear models with additional features. For example, consider a new feature instead of just taking x1 to add like x1 squared. And in this case, we can fit this kind of curves. But anyway, we have to specify it, these additional features by ourselves. And so it can be complicated if you have a lot of variables and you don't have any strong opinions about what your relationship looks like. And then we are interested in something that is more flexible than linear model, but still good at the solving of this prediction problem.
Oh, may I ask a question?
Yes, sure.
I mean, can't we just say, looking at the data, that, for example, beginning from the some value of x, we can say that for example, the right branch of our data can be predicted with linear model. So we can just make two linear models and we can predict data, no?
Yeah, it is an interesting idea. So idea is, for example, to split our data by some threshold and then fit two different linear regressions here and here. Basically, yes, you can do it, but it is not extremely popular. There are models that are called like local regressions, when you fit, when you just kind of use some window and fit your regression models in this window, and then you use different window, and then you fit your regression model in this window, and so on. So yes, there are such methods, but they are not so popular nowadays if you solve just the prediction problem. Why? Because there are methods that work better. and we will discuss these methods now. Yeah, they are, in a sense, they are very similar to that you proposed, but they are, in a sense, even simpler. So you proposed to split our data set into parts and use two linear functions here and here. And regression and decision trees, you probably heard about them. They just use actually the same thing, but they do not use linear regressions here, but they use just constant predictions at each section. In fact, it appears to be even better. It can be a bit paradoxical because we use, well, it is strange to approximate some functions with something that is constant, but it works. Not just a vanilla decision trees, but their modifications, algorithms that are based on these decision trees. Probably you already heard about decision trees in some machine learning courses. You have machine learning course for the whole group, right?
Yes.
And do you have decision trees there?
We have discussed them a little.
Okay, so probably what I will say now, probably it is already probably you are already familiar with it, but let me just to make sure that everybody understand them. Let me reiterate a little bit. So the first thing that I want to discuss is the decision tree algorithm. Actually, there are different versions of decision tree algorithms. Actually, this is usually called CART. Decision tree. Decision trees can be used to solve different types of problems. I mean that they can be applied to data when you have to predict some numeric value, and this kind of problems is called regression problems. And also they can be used if you have to predict some categorical value, like in logistic regression, and in this case this is called classification problem. So prediction problems. This is actually not related to decision trees themselves. This is a general classification of prediction problems in machine learning, and they can be subdivided into regression when we need to predict numeric value, and classification when we have to predict categorical value. And decision trees can be used to solve both of these problems. So classification problem is an example of an algorithm to solve classification problem is logistic regression that we discussed previously. And an example of regression problems is the problem that we solve with linear regression.
Oh, can you please explain the difference between regression and classification? Because I mean, we say that regression is predicting a numeric value, but can't we say that classes are also just numeric values, and then we just predict these numbers? So what's the difference between them?
Sometimes, yes, sometimes it is possible, but sometimes we better. Well, basically, yes, it is possible just to encode in any classification problem. It is possible to just make kind of label encoding, encode your class that you want to predict with some numeric value like 1, 2, 3, 4, 5, and then consider it as a regression problem. But not every time it will work good. For example, in regression problems, we assume that there is some structure, there is some order and some relations in the values of the variable that we want to predict. And in classification problem, we often lack this structure. We don't have a relation like one class is larger than another class. One class label is larger than another class label, or twice as large. So it is possible to use, but probably it is just not the best choice. But actually, the algorithms are very similar. So probably you know already how these decision trees work. Can anybody explain how a decision tree works?
We just so we try to split the data. For example, we have at first one large piece, and then we try to split it into two halves. Not two halves, but two parts, and so on. So we try to split the data each time the better we can.
Yes. Basically, okay. This is correct. Let me just recall that if you already have decision tree, it looks like the following thing. Assume that, okay, assume that I have some data. I will draw data for a classification problem just because it is easier to draw the corresponding picture. Assume that I have two independent variables, x1 and x2, and I have some data, like I have some points here. And I have some points here. Something like this. So I have two class classification, and this is class 1, and this is class 2. And this is my data. And then probably I have some decision tree that works as follows. Okay, let me put some numbers here. For example, 1, 2, 3. And 1, 2, 3, 4. Something like this. And then I can create the following decision tree. For example, it can make the following decisions. First, it asks, is it true that x1 is larger to some value, like 1? And then it gets an answer. And according to the answer, it makes, it can do one of two possible things. Either it can just give a prediction. For example, if the answer is no, then it can give you a prediction of first class. And if the answer is yes, it can continue splitting. For example, it can split by which condition would you like to add here? which condition to check. Any ideas?
If x1 is less than 3.
Okay, yes, possibly. X1 is less than 3. Okay, actually, let me use this larger than 3, just for uniformity. Then we have again two options, no and yes. And if it is yes, what is our prediction?
Class 1.
Yes, this is class 1. And here, if the answer is no, then what is your next question?
Is x2 more than 2?
X2 more than 2, right? And then, for example, we can stop like if x2 is greater than 2, then we are somewhere here, and our prediction is class 2. And here, our prediction is again class 1. So this is the regression tree, and when this regression tree is drawn, like on this picture, for every new point on the plane, you can just follow these lines and get and finally get a prediction. So basically, this decision tree defines, well, mathematically speaking, it defines some function that allows you to calculate these predictions in in arbitrary point of your space of your features of your variables. In a sense, this tree corresponds to the following splitting of the whole space. So first I split this by x1 greater than 1. Then this splitting, and then this splitting. And I can draw the following. I have these predictions here, here, and here. And I have these green predictions here. So we divide everything into such areas. And this is how decision tree works when we want it to predict the outcome. Then, okay, so is it clear? Are there any questions about this part? Okay, I believe everybody's seen pictures like this already, right? Okay, so the next part, what if we have data and we want to construct this tree? How to do it? You see that at every step here, we choose a condition or a predicate that asks, is it true that some value is greater than, some variable is greater than some value, some threshold. If it is categorical variable, we can do it in a different way, but let us now, for simplicity, discuss only numeric variables. So we have only conditions like this. And then at every stage, we have to find this conditions. So we have to find which variable to choose, and we have to find the thresholds with which we compare this variable. So how to do it? Do you know how to learn a tree? And you want to construct?
We should choose a criteria, for example, or entropy or Gini criteria, and we should choose the variable which explain our data the best. Yes?
Mm-hmm. What do you mean explain the best?
Split our data on the best way.
And how do you choose which way is the best?
We should look for each variable. We should look at how clear the split is, how many objects are in not their class with this variable.
Mm-hmm. So yes, yes. Let me just repeat this thing. If you have, if you just have some data set, assume that we construct this tree from top to bottom. So we just choose this condition, then this condition splits our data set in two parts, and then we continue with each part separately. This is called greedy algorithm. And in card, trees are learned by this greedy algorithm. Basically, this is not the only option how to learn tree. Probably you can construct different algorithms, but greedy algorithms works pretty well in this context. And so you just have to define how to find one best split. And this is actually done in the following way. For classification problem, indeed, we have a problem like this. We have some values of two classes. Okay, let me use the same symbols as previously. We'll just copy a part of this picture. And then I can split this part of data in different ways. And for example, I can split it like this, or like this, or like this, or like this. So many different options how to split it. And what I really want is to split this data into two parts such that in each part I have only objects of one class. So my goal is to split to two parts such that each part is as close as possible to a part with only one class. This is reasonable because in a perfect situation, after this split, I just will give predictions for one part and for another part. And I will be happy if I can just say that, okay, I see that all data from left part belongs to one class and all data from another part belongs to another class. And this is my predictions. So I want to estimate this thing. What does it mean to be as close as possible to a part with only one class? And this can be done in a different way. So for classification problem, we have two popular options. So we introduce the so-called impurity function. Impurity function measures this thing, how close our class, how close our part of the data set to this this thing. And popular impurity functions are Genia. This is the following function. Let us assume that I have, for example, objects of three classes like this, this, and this. And then let pi is proportion of objects of class I in my data, in my part of my data set. And then Gini function is the following thing. Basically, Gini is the following function. Let me predict, let me use as a prediction random class with probabilities pi. Then Gini is an answer to the following question. What is probability that I predict correct class? No, incorrect class. So what is probability to make a mistake if I just choose a random class from these possible classes, and probabilities are just proportional to number of elements in the corresponding part. So in this case, for example, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So for example, here I will choose this with probability 1/3, this with probability 2/9, and this with probability 4/9. Then what is probability that I predict incorrect class? If the correct class is chosen according to the same probabilities. Can you find it? Anybody?
So it's one. Oh, sorry.
It's 1 minus the probability it was correct?
This is true, but it is easier to find this probability explicitly. So, for example, I have probability 1/3 that I will choose this class. What is my probability to make a mistake in this case?
2/3.
2/3, yes. And there is a probability of 2/9 that I will use this class. Then the probability to make a mistake is equal to 1 minus this thing, and it will be 7/9. And plus 4/9 times 5/9. So the general formula is like this. And you see that if I just have all elements of the same class, then this thing is equals to 0, because this thing will be equals to 0. And it is possible to prove that this thing will be maximum if I just have the same proportion of all classes. So this is Gini. And another impurity function, another option is entropy. That is similar. I will not explain now why this formula looks like this. This is some story about information theory. Probably you will discuss it with Nina sometimes. But this is a function that actually looks very close to this Gini, works more or less in the same way. Proportion as in the part that we choose. So we want to estimate how far our part to some perfect part for which all elements has the same class. And so we will find the value of the impurity function that can be Gini or entropy or probably something else for both parts that we have after split. And then we can find something like, so we have how to make a split.
Oh, Liz is asking something in the chat.
Yes, I think I answered the question.
May I also ask a question?
Sure.
So we just try to understand how well we split the data, and we have
Yes.
like if we have two classes, we have two spaces or something like two splits, and we count entropy or Gini for both of these parts, right? And what do we do with them next? We just make a sum of them and divide it by 2, or how does it work?
Yeah, I will explain it now. So I just discussed only how to make one split. So Andrea, ideally Gini should be equal to 0. Yes, because 0 corresponds to the case when we just have only one class. But for example, if we have 3 classes, it is better for us to have, for example, class 1 and class 2 and remove class 3, rather than to have three of them. So using this Gini, we can compare distributions with several classes as well, or using entropy. So how to make a split? First of all, we can choose some variable. And choose threshold, variable xi, and threshold ti. So I have my data. And I make some choice of variable and threshold. For example, I choose x1, and as my threshold, I choose this t1, this particular value. Actually, if I chose a variable, then I have only a finite number of ways to split this data set, because I have finite number of elements in my data set, and I can just try every possible split. And this is just a finite number of splits. So I fix some t, and then I find our impurity function of both parts. So let me denote, for example, this. Let me denote this part as left and this part as right. So I find impurity function of left part and impurity function of right part. Also, I have to take into account the number of elements in each part. So let me just to multiply just by, for example, number of elements in left part times plus number of elements in the right part. So this is number of elements. And this is impurity function. Gini or entropy. And then, so for fixed variable and fixed threshold, we have some concrete value of this expression. So we can just find it. It is just a number. And then we just iterate over all possible splittings, over all possible choice of x's and t's, and just minimize this value. So I just select those split that gives you minimal value of this thing. And this is the splitting of one part of the data. And after I do this split, I have to decide. For example, I did this split, and for example, I use this split for my data. Then I have to decide for both parts, for left part and for right part. I have to decide what to do next, and I have exactly two options. I can either say that, okay, I stop at this part and I will make a prediction, or you can say I will split this part once more and continue the process. If I decide to continue the process, it is continued in the same, exactly in the same way as described. So for example, I can say, okay, I will split this part again, and then I will find all again, I will reiterate over all possible splits, and I will find the split that is best fit according to this criterion. So the question is how to make this decision. when to stop. Basically, different algorithms can use different different stopping rules. This is called stopping rule, and it can use the following possible rules. For example, minimum number, or better to say, okay, if number of objects in part less than some value, stop. Another option, if another option is to limit tree depth. So if I have a tree, I have its depth. So how many questions I ask before I make a decision, before I give an prediction, and we can limit this depth. Just say, if I already asked 5 questions, I have to stop, no matter what. Basically, it is possible to use some other ways, but in R there is a popular algorithm that use some statistical test. So we can test, like we do something like chi-squared test, and just try to test, is it true that we have some statistically significant relationship between the variable that we want to predict and our variables. For example, we can just make it in a different ways, but we can just make some kind of statistical test. So we can statistically test so we have null hypothesis is that the predicted value or target value does not depend on our axis. And if we can reject this, then we continue. And if we cannot reject this, then we stop. And this is what is actually implemented in C3 function from R that we will use. Actually, this is rather nice idea, because it allows you to make this decision, this stopping rule more or less automatic. Because, for example, if you use scikit-learn in Python, and you use decision tree there, then you have to specify this kind of stopping rules explicitly. Just when you run this classifier, then you have to specify it, or just use some default values. But anyway, they are specified. But in this case, it is a bit more automatic, and in some sense, it makes sense to use this statistical test, because if you don't see any statistically significant dependence, probably you just have to stop at this level and just say, just give some prediction, because you don't have information in your variables to make some better conclusions. So this is basically how one tree works. Are there any questions here? Okay, just give me a second to turn on the light. Actually, this is basically a rather simple algorithm, and it allows you to make some predictions for any data set, and it gives you any, it allows you to take into account any kind of nonlinear relationships between variables. By the way, I didn't discuss it, but if you have if we have regression problem, it's almost the same. So in the regression problem, basically idea is the same, but when you decide what to predict here, if you have classification problem, you just look at a particular part of your data set that satisfies this condition. For example, at this part of the data set, and you choose as a prediction the class that just gives you a majority in corresponding part. For example, if my part is this one, then I will select class 1 as my prediction, because the majority of elements here belongs to class 1. So in this case, the choice of the prediction is just like a voting, just like a majority voting. And in the case when you have to predict some value, you just you probably can just choose an average of all values that lie in the corresponding part. So we have the following differences. Make a prediction based on an average value of all y's of objects in the corresponding part. And the second difference is impurity function. What to choose as an impurity function in the case of regression. So in this case, you don't have some classes, but you have just values. And what to choose as impurity function. Again, I want my the content of my part is to be as close to a constant as possible. How to measure deviation of values from the constant.
We can count it as a dispersion using this constant as just мат ожидания.
Yes, exactly. This is we just use well, sample variance. Impurity function is sample variance, or it is proportional to residual sum of squares. When you select as your prediction, you just select an average. And then residual sum of squares is the sum of squares of differences between your values and an average. This is a value that is proportional to sample variance. Exactly. So there are only two differences between classification problem and regression problem. And you can use trees for regression problems as well. There is a problem with tree. The main problem with tree is that they are too flexible. So they overfit. You know overfitting from machine learning, right? So you can overfit if you don't make some clever stopping rules. For example, if you allow your tree to grow indefinitely, then you can fit perfectly to any data. This is in contrast with linear regression, when you, more or less in any case, you have some discrepancy between your straight line and your data. In regression, in trees, you can overfit. You can fit any data that you have. This is no problem. But again, if we have a model that can fit to any data, this model most probably will be useless, because what you are interested in is not a data, but some underlying relations between variables, and some relations between variables in the population. You are interested in some data generation process and not the data themselves. So if you have model that perfectly fits to data, this model will be not very good to explain and predict some new data points that are taken from the same population, but not from our data set. So the problem with trees is that they can overfit greatly. And possibly it is a reason why people don't try to use this kind of models, because these models, when you allow to fit some regression on each part, to predict not just a constant, but predict some kind of regression, these models are even more flexible. So probably they can overfit so probably they are even more prone to overfitting. But I'm not sure. I never tried to work with this kind of models. Anyway, the problem with trees is overfitting, and there are different ways how to deal with this problem. And one of the popular way is random forests. So do you know how random forests work?
We just built a lot of trees, which are not very big, so there are not a lot of levels. So having lots of trees with different classification thresholds can help us choose can help us to predict with no overfitting. No?
Yes, but okay. If you have a forest, then probably this forest contains a lot of trees. But why these trees are different? How to train different trees?
If I'm not mistaken, it's because we take different batches of data to train different trees. This is why we get different splits.
Yes, actually, there are two ways how to do it. First of all, what is our basic idea? The basic idea is the following: we want our model to be, in a sense, a bit more robust. I mean that we want our model to model the relation in the population, but not in our particular data. So the idea is that we can generate a new data from the data that we already have. And in this way, we can fit different trees, and these trees will be different. And idea is that they will probably give a little bit different answers. And by averaging of these answers, we can make a better predictions of the values, not in our particular data set, but the values that will correspond to the average value in the population. This is like when we want to estimate some quantity in the population, like if we want to estimate like average height of people in some city, we select a sample of people and then make average of this sample. Here we do more or less the same. We use the same idea of averaging of several more or less independent predictions. But to make these independent predictions, we have to do some kind of randomization of our data. And so to train a random forest, we have to do the following thing. First, we have to bootstrap the data. What is bootstrapping? It is the following procedure. I have some data initially. And then we can say, okay, I want to, well, in a perfect world, I will just get another data from the same population. But I don't have another data from the same population because I don't have access to population. I have only the data that are already collected. I don't want to go again into my expedition and again find informants and ask them questions and so on. But I want to make, in a sense, a new data. And the idea of Bootstrap is that you can use the data that you already have as a new population. And you can get new data from the existing data just by random choosing of elements in this data that you have. So you do it in the following way. For example, I pick a random element of my data, random row of my table. For example, I pick this row. Then I say, okay, this row will be my first row of my new data set. And then I continue and I do sampling with replacement. It means that even after I said that I will use this row as a new row of my table, of my new table, I can pick it again. Anytime when I select a new element here, I just pick a random element from my original data set and with equal probabilities. So it is possible, for example, for this element to be chosen twice, for example, as this element and as this element, or more than twice. It means also that it is possible for some elements to be not included into my new data set. So some elements will not be included just because they are unlucky. When I do this selection process, I just chose this element 0 times. Then it will not be included into my new data set. So yeah, Bootstrap is the procedure of sampling from my sample with replacement. And in this way, I create a new data set. Usually it is a data set that has the same number of elements as the initial. But it randomly differs from my initial data set. Some elements are included twice, some elements are not included at all. So there are some differences. So this is the first way how we can randomize our process. Are there any questions about this Bootstrap? Okay. The second thing that we can do is to randomly choose only part of variables. So let me recall that when we created a tree, at each step we decide which variable to put into my condition and decide the corresponding threshold. But in random forest, before we make this choice, we say, okay, at this state, we can choose only, for example, x1 and x3 and x4, and we have to ignore x2 and x5. So we just temporarily remove some variables from our data set when we make the choice of this condition. And we do this procedure at every time. So for example, probably here we chose only to use these variables. And here we chose to use these variables and so on. So again, we add some randomization, and this randomization have to make predictions of our random forests in a sense as much independent as possible. So we want this. In this way, we want to make predictions of our trees in our forest as independent as possible. So we want them to we want them to make some random errors in their predictions, and we want these errors to be independent. So when we make this, when we average their predictions, then we will kill their errors. So this is why we want these two ways of randomization when we learn every tree in our decision forest. So let me reiterate. We have in decision forest, we create a lot of trees, for example, 1,000 trees. And each tree is learned on its own version of the data, on its own bootstrapped sample. And during the learning, we use also this randomization of features. So we allow our tree to use only a particular features at each step, again, chosen randomly. And in this way, we create a lot of trees that try to predict more or less the same thing, but based on a little bit different data. And in this way, the predictions become more independent. And then we use, so when we use these trees and we use their predictions, so if we have new element, we just put this element into each tree and then get the predictions of each tree, and then we average these predictions. Either if we have regression problem, we just can take an average, just an arithmetic average. Or if we have classification problem, we can just make these trees to vote for a particular answer. So we have to average predictions of each tree, or let them vote in classification problems. So this is how random forest work. Are there questions about random forest? Okay. Basically, if we compare models like random forests with models like regression, as I mentioned at the beginning, we can, well, basically, the main difference is that models like random forest can catch any nonlinear dependencies, but also they are much less interpretable than linear models. Because okay, if you have just one tree like this one, then it is more or less interpretable. At least you can draw this tree, and you can, if somebody asks you why tree made this decision, you can just say, okay, because it checked this condition, then this condition, and this condition, and it make a decision according to these conditions. But if you have 1,000 trees in a random forest, it is not very obvious how to find some interpretation of the result. So random forest says that it uses it gives you some prediction, but if you want to ask why the prediction is like this, you cannot give some good answer for this question. So we don't have a very good interpretation of random forest, but at least one thing we can get from random forest thing is called variable importance. Actually, there are several ways to find this variable importance. This is roughly, very roughly corresponds to the idea of significance of variable in regressions, but a little bit different. So basically, you can ask your random forest which variable was important in their prediction and which variable is not important. Which variable was used in their prediction and which variable wasn't used. Or better to say, the usage of which variable improves the quality of prediction, and the usage of which variable does not improve the quality of prediction. And this can be done in different ways. And I think that the method that is used in C3 that we use in R is somewhat of the following. We fit all the trees. Then we select some tree. If we fit our trees on bootstrapped samples, then for each sample, there are elements that are not chosen during our bootstrapping procedure. So there are some elements that we just didn't choose when we created this new data set. And this is actually a great feature of this bootstrap procedure because it allows you to test your resulting model on the data that was not chosen by this procedure. So on the data that model didn't see. So you basically get some data for cross-validation for free. You don't have to make explicit train test split. Just because you have a natural test data set, it is just a data set that consists of elements that are not included to our new sample. So this is called out of back testing. And so we have out of back sample. These are elements of original sample not included. Into our train sample. And then we can test how good our tree is on this out of back sample. And then to measure how important is a variable, we want to do something like this. We want to estimate how performance of our tree decrease if we remove this variable. So the variable is important if our predictions, if the quality of our predictions relies on this variable. So if we remove this variable, if we remove information in this variable, the quality should decrease. This is the idea. But how can we remove variable? Basically, if we already have a model and this model already fitted to some data, we cannot just remove a variable from this model. This model needs this variable because otherwise it will not work. And to do it, we just do the following thing. We shuffle values of the variable under consideration. So if we shuffle this variable, it means that no relation between this shuffled value and your y. I mean the following. Assume, for example, that we have variable x1, then x2 and x3. And here is variable y. And in our initial data set, we have the following. Relations. So assume that your data set is this one. Then I will give your a new element, like 15 to 3. What will be your prediction of y?
18.
Yes, 18. So you see that in this data, you have a very good correspondence between these two variables, and you don't have any useful information about this variable, for example, in this variable. So now let me use instead of, let us assume that you learned about this relation from this data. And let me assume two possible new data set. In one data set, we have initially, so let this be your train data set. Now we have test data set. And let us assume that in test data set, we have the following values. So this is our initial test data set. And then let us shuffle X1. If I shuffle X1, it means that I just put a random order here. Let me assume that in this shuffled version, I have the following. I shuffle only one variable. Okay, let me add a new column here, a new row here, just to make things more pleasurable. And assume that I shuffle everything here, and now I have something like this. So let us assume that you trained on this data set, and now you see this data set. What will be your predictions?
8, 15, and 7.
Mm-hmm.
So, by the way,
you
say we just shuffle the X1. So do we look something like, how to say that? So will it be okay that, for example, after shuffling, we'll get just the same results for X1 as before? Or do we try to catch this deviation?
If you have reasonable amount of data, it is highly unlikely. If you have only 3 elements like here, it is possible that you have here the same value as here, yes. But on practice, if you have 100 elements, it is highly unlikely.
But so we shuffle only once, or we shuffle
no, we
times?
we shuffle a lot of times. We shuffle a lot of times, and then we find average drop of average decrease of prediction quality.
And if the task is just to check the importance of a variable, do we really need to play the data into test it and train? Maybe it's a bad idea to have a very good understanding of the data itself. So we just can let overfitting even, and then try to shuffle all the variables one by one, and then just look how the quality of the prediction will decrease. Will it work out, or is it better to split into test and train?
Well, I'm not sure about the general question right now, but In case of trees in the forest, you have your test sample for free. It is just out of back sample. So you just can use it. You just don't need to do any additional splitting. Just because you can use those samples, those items that are not included into your training sample during the bootstrap procedure. Okay, so we see that if we shuffle this variable x1, we will get a large drop of prediction quality. Here, we will predict exactly correct, and here we will have a huge drop. But for example, if I shuffle x2 and keep x1, I will not have any drop of my quality of my prediction. So in this way, we can see formally that variable x1 is important and variable x2 is not important. Actually, it is a popular universal way how to test importance of variable in just any possible setting. If you can do this shuffling, and if you have some test data set, you can do it like this. Actually, this is not the only possible way to do it, but currently I like this method because I think it is very reasonable. Another way is, for example, to count how often a variable is used during the construction of our trees. This is another possible way to do it. Another way is to count what gain of, well, we can measure how our prediction quality was increased during every step of splitting and attribute this increase of prediction quality to the appropriate variables. These are methods that are used in scikit-learn, I believe. They are also reasonable, but sometimes they are prone to some problems. So I think that's all that I wanted to discuss today. Are there any questions?
Oh, okay. So what can be the problems if we use that thing like if a variable is used often, then we think it's important? What can be the problems?
Well, for example, if you have categorical variable with a lot of levels, probably it can be used more often just because you have a lot of levels. Actually, I'm not sure that I can give you an exact example right now. I can give you some references where it is written.
Okay.
Okay. So in this way, you can compare your variables and get some information about which variable is more important for your predictions. Okay, are there other questions? Okay, so probably it was known material for you, but probably it is not a very bad idea to repeat something that you already know. Okay, yeah, so after 10 minutes break, we will continue with some practice in R. So stay tuned.
Thank you.
Thank you.
Bye.
Thank you. Bye.
Thank you.
Thank you.
Thank you. Bye.
I think it's time to
Well, we launch our class, and today we'll look into 3 case studies with, well, similar, kind of a similar design. But first we'll look at the code and see what kind of packages and code we need, and then there will be 2 other case studies. You can just do it yourself and interpret the models. Okay, so for today we will use the library party. Actually, there are lots and lots of packages for this kind of cart approach, classification and regression trees. And some people prefer random forest, some others things like RPart. But today we'll look more into the party. Okay. Okay, and the first case study you are familiar with, but I just well, make some points here. So this study was about the consonant drop in Russian. We already discussed that in Russian, some complex character chunks, such as STV, can be simplified. And in this case, we will pronounce бесчинствовать as бесчинствовать with the V drop. And well, our student Varya Sveshnikova decided to check whether this consonant drop depends on some other variables, other predictors. So her idea was to investigate whether the word under analysis matters, and whether the position of the V matters. In this case, she split her data into 3 groups. The first group was in the position of infinitive of the verb, such as бесчинствовать. The second was in the first person singular verb form. And the third one was in the position of the deverbal noun. And the third criteria was to check whether the stimulus was pronounced in a strong position under logical stress, such as я не бесчинствую, yeah, or in a weak position. So the idea was that weak position would allow much more drop of V rather than under logical stress. Okay, so today we will fit a cut model using C3 function first. So we will fit the decision tree and visualize it. And then we'll fit a random forest model, and we will run it with some controls. So we'll look into that. Okay, great. So first, please read the data. And now we will just run the decision tree model with the default arguments. So in this case, we just put the model. We show the model that we are interested in V elision variable as a dependent one, and all other variables that are present in our data set will be used as predictors, or rather as a split criteria. Okay, and now let us plot our model. And as Ilya already said, well, decision trees are a great tool for interpreting what happens in our data. So sometimes they are not that great in terms of the model performance, but they're very easy to interpret, especially if you have a moderate number of predictors. So first, let us look at the general tree, like here. And here you see that all nodes are enumerated from 1, 2, 3, 4, 5, 6, 7. Yeah. And there are some terminal nodes we are interested in. And our tree is always binary here. So when we have 3 groups, the first split will be done, well, between the 3rd group and 1st and 2nd. So we see that the groups, the split according to the group criteria is made in 2 steps. And actually nodes 6 and 7 are just achieved with just 1 decision rule, which is technically done in 2 steps. Yeah, so we see that if our example belongs to the 1st group, then we see that all stimulus we have in our data set are actually get the no label. And here we just see the number of observation in this node and some idea about the probability of yes and no in this group. And as for the 2nd group, we also see a high probability of the no label and so on and so forth. Well, but usually we need much more information, especially if we have more variables in our data set, more predictors in our data set, and we sometimes need more information. So in this case, apart from plot fit function, we can also use print fit function. Actually, here we just see the same information. We also see the number of observations, which are called weights here. And we see some other information. And one more useful function here is just the argument type equals simple. The so-called simplified view of our decision tree. And this is of course very useful when we have a lot of predictors in the model. So here we just get the probabilities in our terminal nodes and can see what happens here. Well, and now we'll look how this works with the predict function that works just the same way as with other models we see before. So we can, first we can predict just one point. So we give some observation and get the response. So in our predict function here, we use response equals true in order to get the prediction. And now let us do the random forest model. Here we will use the same formula for the model. So we are going to predict V elision against all other predictors present in our dataset. And we will control for the number of trees in our forest and the number of trials. And just remember that if you want to get the same result as in my file, you have to fix the randomizer. Set seed equals something, and then we'll get the same results. Otherwise, you can get slightly different results. So here I just put my data set in the cforest function, yeah, and get prediction for my cforest model. And it is important to use the OOB out of bag argument to get the prediction here. And the last step here, now we will use varm function. This is a function within the party package, but you can also use other variant functions from different packages. And there is a particular package with imp with uppercase I, created specifically for measuring the variable importance. So now I take the VI variable, create the VI variable. And here I just include, well, the variant function measured on the results on the fit of my random forest model. Then I ask the model to sort my variables according to the variable importance and just print it as data frame. So what we get here? It was probably obvious from the decision tree that group was very important in our well, decision rules. Yeah. So, well, group has the highest position in our list sorted according to variable importance. Position is the second one and word is close to it, but still the same thing. It's useful to know that, well, variable importance is a matrix which is not standardized here. So it actually depends on a lot of properties of your model, and absolute numbers like 005 or 072 doesn't say us anything. So we just look at the hierarchy and, well, sometimes see if there are some subgroups of variables in terms of some more important cluster and less important cluster. I think that here we can say that according to variant function, well, group can be interpreted as the most important variable, and there are two variables that are less important. Any questions so far? Well, sometimes, well, I can see advice such as replicate your random forest in order to see whether the variable importance results are stable. And if they are not stable, then just increase the number of trees included in your model, or, well, do more permutations. And in our case, when we replicate our fit 10 times, we see that the results are quite stable. And the last step here, we just, well, measure the model accuracy. So we use the predict function and get the vector of predictions according to, well, yes or no class in VLesion. And then can look at the accuracy table and see whether we have false positives and false negatives. So this is a confusion matrix here. Well, and, well, calculate metrics such as accuracy or whatever metric you want from the confusion matrix. Well, in our case, our, well, random forest model gave us accuracy about 80%. Okay, and let us just, well, get a bit back and, well, look at the question 1.3, yeah, where we were asked to predict a value of the word per page in the third group. So now you can, well, look at the data set and choose another route, yeah, and, well, try to predict a value of V lesion for just another observation point. Folks, any question for now? Just ask me or raise your hand or write down something in our chat. Okay, if you're fine with the first case study, I think that we can go on and consider the second case study. It is also about, well, consonant drop or deletion. Well, and, well, it is about how S consonant behaves in some dialects of Spanish. I just, well, give you a short explanation what kind of variables do we have here. We see that there is a class of grammatical categories. The author looked at 5 grammatical classes, whether S is used in some monomorpheme, some very free morpheme in verb, determiner, adjective, noun, and so forth. And then the second very interesting class is of the speakers. Yeah. So, well, according to Henrietta's hypothesis, well, S can be deleted in some social register, whereas it can be stable in another social classes. And phonetic constraint is also important here. So now you can read the second data set and do the same kind of coding and, well, fit both the decision tree in order to get the first idea about your data, and then run the random forest model. Just take your time. I think that, yeah, we can, well, discuss it in, say, about 10 minutes. Ань, во-первых, попробуйте прочитать просто через точку, как read CSV, потому что read CSV, вот эта старая функция, она как по дефолту все ваши переменные старается сделать факторами. У меня есть подозрение, что проблема, собственно, не в переменной, которую вы сейчас, значит, смотрите, s-deletion, да, вот, а проблема, скорее всего, в том, что у вас другие классы тоже не являются факторами. Или действительно в явном виде задать тип переменной для каждого столбца в вашей табличке.
Хорошо. Получилось, спасибо.
Хорошо. Ну что, не обсудить ли нам то, что у вас получилось? Есть ли люди, которые уже смогли сделать второе задание? Или лучше дать еще время? Так, Лиза спрашивает, что пик, который обозначается на дереве решений, это вероятность чего? Это значимость вот этого конкретного критерия, этого сплита, собственно, который измеряется, ну, как обычно, любая значимость. Дело в том, что вот чем метод деревьев решений хорош и чем он в то же время плох, что нам как бы дают обычно готовый ответ, и обычно люди на нем и останавливаются. И на самом деле все другие сплиты, которые дерево видело, но посчитало статистически незначимыми, они здесь не отображаются. На самом деле одним из параметров вот этой модели может быть, естественно, немножко подвигать этот движок и, в частности, попросить, чтобы вам показывали и p-values, которые там уже явно больше, чем выбранный уровень альфа. В данном случае мы это интерпретируем, что, например, consonant, да, критерий говорит нам, что в этом случае деление вот на две такие группы, consonant против pulse и vowel, оно рассматривается как статистически значимое. Насколько я помню, по умолчанию стоит 0,05, как такой стандартный критерий, но опять же надо посмотреть в справку по функции. Давайте я пока задам вопрос на понимание. Почему, ну, я не хочу задавать вот вопросы типа сколько точек наблюдения в шестом узле. Я думаю, что это слишком просто для вас. Но вопрос другой. Почему нельзя спросить, в каком из узлов вы видите конкретную t-статистику, такую как 61.559? Почему про это спрашивают там, где мы смотрим на дерево решений, но не там, где мы смотрим на Random Forest, случайный лес?
Может быть, потому что в лесу слишком много таких деревьев, и не очень ясно, как определить. Ну, то есть там у одного дерева может быть, допустим, P1, у другого дерева другая, и не ясно, как их выбрать.
Да, безусловно. В данном случае вот наше с вами дерево решений видит все точки и, собственно, по ним строит дерево. Да? Поэтому, естественно, что здесь, что бы мы ни делали, статистика будет из наших данных получаться одна. А когда мы делаем random forest, то, естественно, тот самый фактор random вот, будет влиять, и деревья будут очень разные. Да, поэтому, конечно, там все статистики будут зависеть от конкретной запуска. what we usually can do with the C3 function, we also can explicitly say that model can use some subset of our data for fitting. And in this case, the model will decide on the number of significant variables in the decision tree model, but then she will fit the data according to some subset of data. Вопрос от Алексея. Статистик, что это в результате? Там разве не категориальные значения? Вот эти статистики, это та же самая T-статистика, которую мы видели в других моделях. То есть это в данном случае просто результат вычисления функции. То есть, по сути, это характеристики того или иного сплита в наших данных, в partition. Да? На практике простые люди, так сказать, ими никогда не пользуются. Ну, в смысле, что просто они выдаются моделью, но не то чтобы они как-то специально интерпретируются с точки зрения понимания тех исследовательских вопросов, которые вы задаете. Давайте я задам более важный вопрос. Скажите, пожалуйста, значит, давайте посмотрим все-таки пока что на дерево решений. Да, вот. И решим, что же, собственно, вот такая базовая модель про наши данные нам говорит. Вот. Я думаю, что даже если... Okay, let us look at the decision tree plot. And, well, I will ask you to describe what happens with the data and what are conditions for the S deletion. Can you say something about some simple decision rules here? Ira says elision is less likely to happen if the speaker is of higher social class. Let us look at the data. Yeah. So we got social classes, and in our case, I think that in my case, the variable social was treated as numeric. So you see the rule that the group can be either one or more than one. Yeah, and we see that, well, in certain position, the social group matters. Yeah, nodes 3 and 8. Yeah, right. And I would also say that well, some phonetic constraints can be even more important, because if we have a position before consonant, when in both classes we see a lot of S deletion. So this is this position favor for S deletion. Yeah, Alexei says if social is more than one and the following segment is a pause, then there is elation. It is likely that there will be elation. Yeah, I think so. Okay, and then, let us look at the results of the C-forest fit. And you see that we asked you to use less trees and less entry, because there are much more observation points in this data set. And in this case, well, if you would use entry equals 1,000 or 10,000, then there could be some, well, computational problem sometimes. So that is what, well, my model says. It says that, well, we can measure variable importance with the random forest model. Well, and now we see that if we run the full model with all three predictors, which is grammatical category, phonetical constraint, and social group, we see that grammatical category is even more important factor than social and phonetical constraint. But I can actually even say why we didn't ask you to run the tree model with all three variables. This is because the tree view would contain a lot of nodes and would be much less interpretable. Yeah, but when we use random forest with lots and lots of subtrees in it, then we just can see that grammatical category is the most important thing here. And of course, if you think that there are some variables are correlated, you can either rerun your models looking at this or that variable or on both variables and see what happens with the model performance, or just, well, decide logically whether you, well, like this or that explanation. And usually if two variables are highly correlated, then we will see that one of them have a very high variable importance metric, whereas another one would be somehow in the bottom of your variable importance list. Okay, I think that we can stop now with coding because we have less than 6 minutes to the end. And if you have any question with regard to the code or cases we saw in our class today, so please ask me. Так, у нас есть вопрос. При регистрации по проекту в своем репозитории или LingData это как-то нужно фиксировать? Да, значит, лучше именно в том, который вы сдаете свои домашние задания. Да. Угу.
А мы можем там создать репозиторий отдельно свой? Или для этого тоже нужны ссылки?
Мне казалось, что вы можете. Вот, вроде бы, в принципе, мы видим, когда вы сдаете, мы видим в любом месте вот этого репозитория. Вот, я могу еще конкретно спросить, вот, может быть, если не получится, то мы тогда просто сделаем отдельный assignment для проектов.
Я сейчас могу просто открыть, посмотреть, попробовать.
Да, посмотрите, да. Угу.
Нет, похоже, нельзя, можно только у себя.
Окей, тогда я попрошу, чтобы нам создали. Ага, спасибо. В любом случае, вы должны знать, что когда вы в этот LingData выкладываете в любую папку что-нибудь, мы ее по-прежнему видим. Да? То есть на всякий случай, если у вас есть какие-то там задания, которые нельзя положить куда-то и так далее, то их можно всегда положить куда-нибудь еще из существующих папок. Ну что, если нет еще других вопросов, давайте потихоньку заканчивать. Вот. И начинать дискотеку. Большое спасибо тем, кто показывал своих котов. Вот. Они очень украсили наше сегодняшнее занятие. Моя кошка уклонилась от своей прямой обязанности. Ну, что делать?
Моя на такое пошла исключительно из-за того, что была голодная.
То есть это тут кладут, видимо, кошачью мяту. Понятно.
Нет, она просто приходит и начинает требовать ее покормить.
А, понятно, хорошо.
Ради такого она даже готова полоскаться. Ну,
ну что, тогда всем счастливо. Вот.
спасибо.
Спасибо, до свидания.
Заканчиваем.
До свидания.
Всего доброго. Спасибо.
До свидания.